Okay, we're going to start our revision for the half yearlies with our 2011 half yearly question 21. If you at times when we're doing this, please make sure you pause the video and attempt the questions, and then we'll answer them together. So to start with, let's have a look at the first question, which is question 21, we're doing now. And the question is that Michael constructed a toy rocket which has a mass of 10 kilograms, of which we're told 6 kilograms is propellant. The rocket's engines burn the propellant at a constant rate, producing a constant thrust of 150 newton, after which the rocket reaches its maximum height, approximately 100 metres, and then it returns safely to the Earth's surface using a parachute. And we're told the data for one particular launch here as shown in the table. Just take a few moments just to highlight to yourself some of the major pieces of information on that in that question. Right, now that you've read the question and we have taken in all the information, we now need to start working out the question itself, which says we're going to calculate the maximum acceleration. Now the maximum acceleration, we're going to use this formula. And it is not a formula that's on our formula sheet, it's one of the ones that we have to memorise. But the acceleration of a rocket is equal to T minus mg on g. And what will happen is that as the acceleration will increase as the mass of the rocket decreases. So when the mass is minimum, when this value here, that mass there is minimum, then this acceleration will be the largest. We are told that the mass of the rocket starts at 10 up there, and it is then reduced down by 6. So the minimum mass of the rocket is 4. So we can just simply now use the information from the question. The T here is the thrust of the rocket, which is 150 newtons. We know that G is 9.8 on the surface of the Earth. This is close enough to be the surface of the Earth. And we know the mass is 4. So take a few moments to calculate the maximum acceleration of the rocket. Right, we should have, using our formula, found that the value is 27.7 metres per second squared. Okay? The second part of our question is to explain the acceleration of the rocket in terms of the conservation of momentum. Now, we're looking at the verb that is used here as explains. This is a high-level verb in New South Wales HSC. We need to make sure that we give cause and effect, and we are going to not just simply make statements, we have to explain statements. So we need to answer the question, which is the acceleration of the rocket in terms of conservation of momentum. So to do this, what are the major things that I need to bring into one question? So let's have a look at some of the major ideas in this question. If I have an object like a rocket, there is my rocket, and it is moving forward, let's say the mass of the rocket is m, and it has a capital V velocity in the forward direction, then the momentum in the forward direction would equal capital M, capital V. The reason why it moves forward is that out of the back is gas. And that gas, if we say that that gas has, let's use a different colour, has a mass m and is moving at a velocity v, then the backward momentum would equal mv. The only difference would be that these would be, the forward would be a positive momentum and this would be a negative momentum. So they would have to be summing to 0. So the sum of all of the momentums must equal 0. In other words, the forward momentum must equal the backward momentum. In other words, this plus the negative of that would sum to 0, because in a closed system, the sum of momentums would have to equal 0. So now we've got this situation that m capital V must equal m little v. Given any time, take a period of time, say a second or a minute or whatever, so we're just going to call that over t for any period of time, we get m times capital V on t would equal m little v on t. Now velocity over time is acceleration, okay? So all velocity over time is acceleration. So this would be, on this side, this would be m capital A, where A is the acceleration of the rocket. Would equal m little a, where little a is the acceleration of the gas. Okay? So the forward acceleration and the backward acceleration will be given by capital A and little a, just to make sure that we can see that they're different. So what do we know this is? This is the forward force and this is the backward force, and they are equal. What happens to the masses in both cases? Well, the mass of this here must decrease. But what is the forward force? The forward force is also known as thrust. Okay. And we know the forward force, the thrust, is created by this over here. So m times a, little m times a, must be constant. And in this case, it's 150 newtons. So if the thrust is constant, so that the motion of the rocket is constant, but we also have a decreasing, let's get a nice car, a decreasing mass over here, then what must happen on the other side, on this side over here, to make it constant? So just tidying this up, if I've got capital M, capital A equals little m, little a, and I know that this m here is decreasing, and I know that this here, this is the thrust, and it is constant at 150 newtons, then what must be happening to the acceleration of the rocket? This must increase to keep this side as a constant. Okay? So to recap, you somehow have to create a answer for this question which starts with the statement that these two things must be equal and opposite. So in other words, the momentum forward must equal the momentum backward. Obviously they're opposite side, but they're equal in magnitude. And then we need to somehow convert momentum into acceleration. So we divide by a period of time, and we get the idea that the force on the rocket must equal the force from the gas. Force from the gas and the rocket is also called thrust, but we know that it's designed that the thrust is 150, it's constant. That's the design of our rocket. So what would happen is if the mass of the rocket over here decreases, the acceleration of the rocket must increase. So take a few moments and use this information to be summarised into that question. Finally, the last question here for 2 marks is asking about the effect of the G-force on a rocket. So hamsters have the same tolerance of G-force as humans, and we have to assess whether it would be cruel of Michael to allow his hamster to be an astronaut in his rocket. So let's just have a look at, remind ourselves what are some of the things that we need to consider in this question. We need to consider that the maximum G-force, let's call it G-force, is 3G. Okay? And we also need to know that the G-force is calculated by G, that's G-force, is G plus A on G. Okay? Where G is the 9.8 of the Earth, and A is the acceleration of the rocket. Okay. So what we need to do is, remembering we calculate the acceleration of the rocket as 27.7, so we need to calculate the g-force for this rocket, which would be 9.8 plus 27.7 over 9.8. So calculate that there. If I just do that in my head, that's 30, 40, it's going to be about 4G, approximately 4G. Okay. We know that it exceeds, therefore, this. If this is exceeded, then it would be not available for human use. Therefore, if it's not available for human use, it would not be available for the hamster, which has the same tolerances as a human. So, would it be cruel? Now, you can answer this also in another way. So, firstly, we have to assess here. So you have to come up with a value, and we have to say that the g-force equals a certain value, which we know is now 4g. So that's the first thing we're needing for this question. And then you need a statement as to why you say it is cruel. Okay? Based on this evidence over here. We can also add the fact that it shouldn't be that you put an innocent animal through this stress, but I think the whole point of the parachute returning the hamster safely to the earth is supposed to alleviate our problem with that. So here we are to assess based on it's cruel because it exceeds the limited that it's greater than 3G, which we say is not available for us. Okay, I hope this helped for this question. Thank you.